So we talked about probability in the last unit, and I mentioned at the time that we're really looking at the kind of probability that is necessary in order to understand the inferential statistics, because there are entire courses on probability that it's definitely more fun than what we did, because you really kind of get into all the little different applications of probability, but we're focused mostly on inferential statistics, being able to draw conclusions about entire populations. So we spent time talking about normal distributions and binomial distributions. We're actually going to pick up with normal distributions, do a little review of that from Unit 1, and then we're going to start to learn how we can apply that content in the context of inferential statistics. All right, so that's a little taste of what's to come. You see this lovely looking formula here on page 50. That's pretty scary looking. It's fortunately something that's built into the calculator, not built in as in you'll ever have to use that formula, but built in the sense that the calculator knows that formula and can work around it. All right, so we'll get into that. But the normal distribution is a continuous random variable whose distribution when graphed is bell-shaped. So it's a bell-shaped curve, right? So, and we knew that. It's centered around the population mean. All right, so the middle value here is going to be the population mean. And then we continue out in terms of standard deviation. So that's what this diagram is really getting at here, but I wanted to actually construct it with you. All right, so we're counting in terms of standard deviation. So this first entry would be mu plus 1 sigma. The second one would be mu plus 2 sigma. And the last one would be mu plus 3 sigma. All right, again, the mu and the sigma, mean and standard deviation for the population. All right. We could also do the same thing going in the different direction, the other direction. Mu minus 1 sigma, mu minus 2 sigma, and mu minus 3 sigma. All right. The empirical rule applies when dealing with normal distributions, and in the first unit, we actually use that rule to determine whether a distribution would be normal. But here we're kind of relying on that knowledge. We're going to be told that a distribution is normal, and we're going to have to know what to do with it, with that information. All right. But to refresh on the empirical rule, we have about 68% of the data lying within 1 standard deviation of the mean. So this is 1 standard deviation of the mean. That's going to capture about 68% of the data. All right, and we're going to learn where these values come from, which is kind of nice. All right, so 2 standard deviations around the mean would capture about 95% of the data. All right, so there's really no easy way for me to use my highlighter to do this without it covering up all the yellow in there, but I guess I can do that. To kind of treat it like a Venn diagram. All right, so that this whole interval here is going to be about 95% of the data. And then the last one would be about 99.7% of the data. It's going to get out of hand real quick now, but let me see if I can. I think blue is going to be way too much here. Maybe I can get a lighter shade. I'll do this very, very light shade of blue. So that would be all of this data here, accounting for about 99.7% of the data, or the overall distribution. So that would be from here all the way about approximately 99.7% of the data. All right, so I mean, the diagram, the pre-printed one below is pretty much the same thing. It's just it doesn't have the explanation to go along with it. It's kind of like just taking it on faith that you know what all this stuff represents. I figured it'd take a minute to do a refresher. All right. So if we know that about 68% of the data exists within one standard deviation of the mean, about 95% within two standard deviations of the mean, and about 99.7 within three standard deviations of the mean, then we could say that a distribution is normal. But if we want to go the other way and say, okay, we know that a distribution is normal, what percent of the data would be between one standard deviation below the mean and three standard deviations above the mean? You know, you could start mixing and matching here, right? And you could also get into decimal values, because it isn't just discrete values of -1, -3, -2, -1, 0, 1, 2, and 3. You could have a -1.728. I mean, we've worked with z-scores that weren't exactly whole numbers. We just didn't have the ability to find probabilities associated with that. We spend a lot of time learning about normal distributions because a lot of what we observe in the real world can be considered distributed normally, right? And so, and there are some instances where maybe it's not distributed normally, but we can transform the data in some way so that it becomes normally distributed, right? So if we have predictable probability methods associated with the normal distribution, then we could rely on that to evaluate real life phenomena. All right. And so that brings us to the standard normal curve. I mean, the bits and pieces related to a probability density function is really important. Like total area under the curve is equal to 1. Every point on the curve has a vertical height greater than or equal to 0, meaning it'll never go below 0. Technically, it'll never actually even hit 0, because this is what we call an asymptote. I'm trying to remember where I came up with this greater than or equal. If it was from a textbook, then it's just not a good textbook, I guess. But also there's the fact that I copied it and pasted it blindly without even thinking. Really, let me just explain this for a second. When we talk about a normal curve, we're talking about a curve, again, bell-shaped, that will extend out to infinity in either direction, a positive infinity to the right, a negative infinity to the left. All right, so this will go on and on and on towards positive infinity. And this would go on and on and on to negative infinity. All right. And it'll never actually touch the axis. All right. So just trying to figure out something real quick. Let's do it this way. I'm trying to remind myself how to mute folks. I think the situation has resolved itself, but that's a skill that I probably should refresh my memory on. But yeah, it goes out to negative infinity as you go to the left. It goes out to positive infinity as you go to the right. But the curve never touches the x-axis. All right, the horizontal axis, the x-axis. It'll never actually make contact. Unless, of course, it could get out to negative infinity or positive infinity, but that's not possible. All right, that's the infinite part of the word infinity. Okay? It's not a destination that you could ever reach. All right, so, but what this is saying here, when it says it has a vertical height greater than or equal to 0, this, and let me get rid of this big circle I drew. This part here is really in a practical sense. All right, sometimes a number can get so small that it's indistinguishable from zero, but it's not technically equal to zero, right? So you have the theoretical part of things, the calculus of it, if you will, where yes, you can never actually make contact with zero, but in a practical sense, if I'm telling you that the height of the curve at a particular point is, let's say, 0.00000125, you're like, well, that's damn near zero. It's not exactly zero, but in the real world, it doesn't have to be exact. We round all the time. All right. So there's the purely mathematical interpretation, and then there's the practical, right? So I would even qualify this by saying technically. But practically, of course, it does. All right. It's like the old bouncy ball. I'll say anecdote, but if you drop a ball, and you don't have to write this down, it's just me kind of like driving a point home. So if you drop a ball from a certain height, all right, so it drops, it hits the ground, and then it bounces up again. And let's say it reaches 75% of its original height. And then it falls again, bounces, goes to 75% of its original height, falls again, bounces, goes again to 75% of its original height, and so on. The and so on part of this would be infinite in theoretical terms. But I don't know if there's anybody who's ever dropped a bouncy ball and let it bounce and observed it never actually coming to rest. If you drop a ball and it bounces, it could bounce to half of its original height, a quarter of its original height, and so on. Eventually that ball is going to come to rest. But mathematically, if I tell you that this is a height of 1 foot, let me just write actual foot. To figure out the new height here, I would take that 1 foot and multiply by 0.75. And then I would take that result and multiply by 0.75. So this would be 0.75 times 0.75, and so on. If you multiply consistently, this is the same idea when we talk about factorials. If you multiply consistently by a non-zero value, you're never going to get to a result of zero. Right? So I could just show you that, a quick demonstration, nothing too fancy here. But start off with a 1, multiply. So the original height was 1 foot off the ground. Multiply by 0.75. I get the height after the first bounce, so the height of the second bounce. Then the third bounce. Then the fourth bounce. Fifth. You see it's getting smaller and smaller every step of the way. And eventually it'll get somewhere very, very close to zero. It's at roughly a quarter of a foot high now. All right, so keep going. Oops. Now it's at about 0.18 of a foot. All right, so like a sixth of a foot. All right, so keep on going. I mean, it's getting smaller, but it's not going to get to a value of zero. All right, so answer time. We'll do it like a couple more times here. See, very, very small. Eventually, it'll get to a point where it's almost indistinguishable from zero, but it's not going to actually get to zero. All right. And, you try it out with one of those bouncy balls. I mean, you don't have to prove that it's that it's eventually going to come to rest, because it will, but you'll get a bunch of bounces in before it actually comes to rest. It'll just, it will come to rest. It's not going to be the case where it's just going to bounce forever. Right. So, and eventually, and it's kind of like, I don't know, when you dribble a basketball, you dribble the ball at like waist height, maybe even chest height, then you bring it down to waist height, then knee height, and then like calf height. Eventually, like, you're dribbling it where there's only this amount of space between the bottom of the ball and the ground, and it's almost like you're creating a vibration of the ball. All right. So, but you could, if you wanted to, you push down on the floor, that ball come to rest. It's never gonna. It's not gonna continue bouncing infinitely. It's gonna stop at some point. All right. But practically speaking and theoretically speaking, they're not always the same thing. We have to make the assumption that the theoretical is just as important as the practical. All right. The standard normal curve standardizes the mean and standard deviation, standardizes the standard deviation, so that the mean is 0 and the standard deviation is 1, so that we label our diagram in integer values from -3 to 3. Right. So instead of working with particular values, we're scaling it down, or we're scaling it towards a mean value of 0, so that it fits the standard normal curve. The idea being that we can compare multiple samples of data on the same graph. Right? And it'll be an apples to apples comparison. I put the recall here, the empirical rule. Kind of tricky because, using that word recall, because I'm sure there's some folks that are like, I've never heard of this term empirical rule. Well, it was unit 1. So that it's September, September, early October. So it's possible. I mean, you heard it, but it's possible that you've kind of atrophied on that. You lost the muscle memory. Right. But I wanted to, more importantly, show you how we could find these values without ever having to memorize anything beyond a few calculator steps. All right. So when I say the probability that Z is between -1 and 1, that goes back to this diagram. Probabilities correspond with areas, right? So the area under the standard normal curve, or even just a normal curve, corresponds to a probability. Area and probability are synonymous, right, in this context. All right, what this is saying is if I have a Z-score, these are Z-scores, of a Z-score of -1 and a Z-score of +1, the area under the standard normal curve corresponding with that, so all this area here, I'm not going to bother with the highlighter, is going to be 68%. So this little shaded region corresponds to the probability that the Z-score is between -1 and 1, and that ends up being about 0.68. Right. So that's the probability notation that gets us to this. But we want to actually, go beyond the probability notation and learn the calculator notation or calculator functions. All right. So what we're going to do here is go into the tool. So if you're in the home screen, you go to calculation, you have the history of all the stuff there. Go to the toolbox, which is right next to clear. Now I'm going to bring it back to the beginning here, the initial landing point in the toolbox. You want to go to, we did this with combinatorics, but and also binomial probability, but we want to make sure that we're kind of all on the same page here. So toolbox, you go down to probability. Hit the right arrow and go to distributions. And then select normal. All right. Toolbox probability distribution is normal. And what I want is norm CDF range. They give you the little breakdown here of what the bits and pieces are. A, B, mu, and sigma. The mu and sigma, I'd like to think would be self-explanatory, but the A is the beginning of your interval. The B is the end of the interval. So when I'm looking for something like this calculation in NumWorks, that's going to be norm CDF range -1, 1, 1, 0. All right. And the reason we say 1, sorry, 0, 1, brain cramp. I also see somebody's coming in, so I got distracted. So 0, 1, and that's because this is my mu and this is my sigma. And it's like, how did you know that? It's all up here because we're working with a standard normal curve, right? So in these instances, they're telling us the mean and standard deviation are 0 and 1. So when I pop this into NumWorks, norm CDF range, you pop in your -1, your +1, your mean, your standard deviation. It gives you a more precise variant of the 68%. So 0.682, 689, 4921. Right. So very, very precise. We tend to just round it to 68%. You could say 68.3% if you want, but you can do the same thing. This time you just go up and hit OK, change my -1 to a -2 and my +1 to a +2, and you'll get your 95% approximately. And then do it again for 3 standard deviations. Yeesh, fat fingers, hold on. There we go. And that's my about 99.7% of the data. And so all of these computations are really things that in the past we've just memorized. But now we're kind of looking at it like, well, I mean, you'd be right in thinking like, why didn't you show us this in the first unit? It would be a lot of calculator steps for just 3% values, right? Because we weren't going to get to this topic until now, which is months later. So, it kind of makes sense to, just believe the percentages are correct at that point, but now know that we can verify them. But this technique also allows us to figure out probabilities for, let's say, weird Z values. There's a reference to a Desmos calculator here. That's fine if you want to use that, but I'll just stick with the NumWorks. So again, it's the same process. Norm CDF range. You could also use norm CDF. I'll explain that one in a minute. Just I find that people like that less. So just looking at this, the Z values between 0 and 1.5. So here's 0. Here's -1, -2, -3, +1, +2, +3. Between 0 and 1.5 would give me this little chunk of area. All right, so what I'm getting here is the probability that 0 is less than or equal to Z is less than or equal to 1.5. All right, we write it as a compound inequality just because it's the most concise way of doing it. All right. It also reminds us what the variable is. So we wouldn't use something like interval notation because that just makes it a little too simple. Right. And it kind of strips away some of the information that you might want to remind yourself of. But what I would do here is, again, use the norm CDF function. All right. Same one I have on the screen, but let me do it from scratch again. So You land here when you go into the toolbox for the first time. If you land in an unfamiliar location, you're like, oh, how did I get into this menu? Just keep hitting the back arrow until you get to that landing area. All right. Then go down to probability, go to distributions, normal. We select norm CDF range. And for this function, I'm putting in a 0, a 1.5, a 0, and a 1. So again, this is norm CDF range 0, 1.5, 0, 1. All right, so these two values are coming from here, and these two values are coming from here. All right, and so I hit OK, and it gives me about 0.433. So that's telling me that the probability that any Z value that could exist on that interval, the probability that it does exist on that interval would be about 0.433. You could also look at it like, this is, based on what I shaded, it's less than half of what I'd have as a whole, right? Total area under the curve is equal to 1. Cut that in half, 0.5. All right, so if I'm just looking at half of this graph, so just this half here, you're really just saying what percent or what proportion of this region do I have shaded? Right. So it's not something you're going to be able to just look at and determine its value in most cases, but you can at least verify that the number you came up with makes sense. Right. Because if I got something like 0.752, that's more than half, and I don't have more than half of the graph shaded, I'm going to look at it and say, okay, I probably made a mistake somewhere. All right. For number 2, there's 2 ways to handle it because it doesn't give you a between. All right. So this is saying Z is more than -3, but there's an implication there that it's got to be less than infinity. So this is the same as saying the probability -3 is less than Z, which in turn is less than infinity. All right. Now, there's nothing practical about infinity, but we can kind of make it a little bit more practical, or at least interpret it in a practical way. So we can't plug infinity into a calculation because the calculator would flip out, but we can plug in a really, really large number. All right. So like I said, there's 2 ways to do this. You could use the norm CDF function. It's just I've found that not too many people like that approach. So I'll go with this one. So we're looking at, again, -3, -2, -1, 0, 1, 2, 3. So if I'm looking at whether I'm looking at it as Z is greater than -3, so more than -3, or if I'm looking at it as being between -3 and infinity, which would be way over here. All right, so you keep going, eventually you get out to infinity. I mean, you wouldn't, but pretend. What I'd be looking to shade here would be everything starting at -3 and going on out towards positive infinity if I could. All right, so I'm looking at almost all of the area. Whatever area over here that's not accounted for, whatever that area is, it's got to be minuscule. All right, but we'll let the calculator do the thinking for us. So norm CDF range, -3. Well, I can't put infinity in. I want to go -3 to infinity, but I'm gonna say -3 to something large. And then the 0, 1. All right. Now, the only question that ever comes out of this is, what do you mean by large? Is 5 large? Is 10? Is 100,000? Well, how big is big enough? So I do my norm CDF range. I plug in -3. I plug in something that I think is large. Maybe I think 100 is large enough. 0, 1. Hit OK. You get a decimal. It's a decimal that seems to make sense in the context. I shaded most of the graph, and I have most of the area because the max I can get is 1. I'm looking at about 0.999. So the question of how large is large enough, that gets answered pretty easily just by running the calculation a second time and making your large number a little bit bigger or a lot of bit bigger. It doesn't matter, but make it bigger than what it was. So let me say 101. All right, I could have put 1,000 if I wanted to, but I'm going to just do 101. If the decimals are identical, it's large enough. All right. So in your two computations where you make a small change in your large value, if the decimals that you get as a result are identical, then you've gone far enough. All right. Because if I did it, let's say I did it with maybe I thought 4 was far enough. I get something that would round to the same thing, but it's not the same decimal. I would keep going. I would keep increasing, incrementing this up until I got no change in my decimal value. See, difference between 4 and 5. It's not substantial, but it's still a difference. I go to 6. You see, it's a little bit different. But if you go large enough, then you don't have to worry about doing that one at a time. It's like that'd be a nightmare. All right. So I start off with something big, something that I know is big, and then increment that big number up by a little bit just to see that there's no change in the decimal. Either way, no matter how you slice it, you're looking at about 0.999. The rest of the questions are just little variants of really the same concepts, right? Because Z is to the left of 1.28, right? So left of, less than. So here's again -3, -2, -1, 0, 1, 2, 3. Here I'm just ballparking this. This looks like it could be 1.28. I'm shading everything to the left of that. If I were to continue this out forever, which I could, eventually I would get to -infinity. All right, so this is the same as saying the probability that Z is between -infinity and 1.28. All right, so we're doing the same thing again. Just we're swapping some things around. All right, so norm CDF range. All right, so my low value is going to be -infinity. So we're running into the same problem we had in the last question. I want something that's negative, but also large. I don't need the parentheses. 1.28, 0, and 1. I always get some folks confused by this. It's not like I intended, but it just happens because when I say negative large, what I mean is a number that has a large absolute value, but is negative. All right. So what I have in mind here is something like -100 or -1,000. Just technically, if you go further and further to the left on a number line, the numbers aren't getting larger, they're getting smaller. Right. So if I compare something like -100 to 0.00125, -100 is technically smaller because it's more negative than the 0.00125. Although when you look at the 0.00125, that feels like it's smaller because it's closer to 0, but that's just, probably overthinking things. All right, so I'm going to do my norm CDF range, pop in something like -100, 1.28, 0 and 1. I get this decimal value about 0.9 roughly, but we're going to round it a little bit more precisely. It looks, I mean, based off of my diagram, that could be 90% of the curve shaded, the area under the curve shaded. That's conceivable, but I do want to test to make sure that I've gone far enough. So I'm going to make this negative. I'll go to -200 this time. See that there's no change in the decimal values, even though I made it more extreme in the negative direction. I'm now satisfied that I have an appropriate probability. So this is approximately, we're going to go 4 decimal places here, 0.8997. It's not like I'm changing the rules or anything. It's just I don't want to lose the degree of accuracy. Because if you take that 7, that makes the 9 go up, makes the second 9 go up, and makes the 8 go to a 9. Before you know it, you're rounding this to just 0.9, and it kind of feels like you've lost a lot of precision there. So for the sake of accuracy, that's what we're going to do. So when you see to the right of, greater than, more than, at least, we're treating those all the same way. Okay, so when I say to the right of 1.00, so here's 0, 1, 2, 3, -1, -2, -3. To the right of 1, here's 1. Talking about all this area here. Again, that's that whole infinity thing, right? Because more than or to the right of 1 could technically go on forever. So that'll get us out to infinity. I'm looking for the probability that Z is between 1 and infinity. So we do a norm CDF range. 1 to something large. 0 and 1. Again, the 0 and 1 at the end are because the mean and standard deviation are given for all these problems to be 0 and 1. All right. So we pop it in. And one of the cool things about the toolbox here is, I mean, unless if you're using the emulator online, it resets pretty much all the time. But if you're using the app, it hangs on, it has a memory, it hangs on to the previous calculation. So when I go into the toolbox, it brings me right back to the same spot that I left off. So it's kind of nice. So 1 to something large. We'll go to 1,000 here, get a little saucy. And I get this decimal. And again, I just want to make sure that I've gone large enough. I'll just throw another 0 on at the end there. Yeah, just don't go too crazy with the large value, because I've had people say, oh, my calculator's broken. I got an error message. And that's because for the large value, they put 100 quadrillion. And it's like, all right, you're going to run into an overflow on the calculator. It's, so don't go too extreme. Just go extreme and then a little bit more extreme. All right, so we're looking at about 0.159. I don't know if that feels like 15% of the graph, but that's also a function of the drawing, so I mean the what you call it, the scale here is just it's out of whack a little bit, the vertical axis anyway, because a normal curve, if memory serves, maxes out at a height of 0.4. So I have it between 2 to 3 tick marks. So, scale wise, it's definitely a little out of whack. Now, the beautiful thing, well, for me anyway, but also you'll find this to be the case, is just you might get aggravated that I'm about to do the copy paste thing. Numbers 5 and 6 are asking for the exact same thing as numbers 3 and 4. They're the same question. All right. It's just kind of packaged a little bit differently. Now, there is the concern about the at least, at most kind of stuff, because when you talk about something being at least, that corresponds to greater than or equal, or less than or equal if you're talking about at least. Right. And so you've always learned in the past that less than and less than or equal are two different things. One includes the endpoint and one doesn't. But the thing is, there is no width at the endpoint. Right. So what's happening? I mean, this is a little in the realm of mind bendiness. But if I tell you, for example, in this case, that I'm looking for the area in the normal curve that's to the right of 1, I'm looking for all of the area to the right of the 1, that line at 1 that I clearly drew as a vertical line with a little bit of width is really a vertical line with no width. All right. So the concept of a line can be tricky, but it's really just kind of a location more than a physical object. All right. So this line has 0 width. It's not like, I mean, it appears like a rectangle, which would have some thickness to it, some area, but that's only because that's what I have the thickness of my marker set to. All right. If I wanted to, I can dial this down to 0.1 millimeters and draw this as the line at 1. All right. It's the same line. It's just how I chose to draw it. All right. And in theory, I don't even think I can go smaller than this. It could be something that's so thin that you can't even see it. All right. So I just drew a line there at 1. And you're like, but I don't see it. And it's like, well, because I drew it so thin that you can't see it.
That's a Seinfeld reference, by the way.
Oh, is it?
Yes.
The drawing of a line?
Yeah, it's about the slicer. I don't know. I'm old. So
Oh,
it reminded me.
okay. I know you.
Sorry.
No, that's good. I'm gonna have to pull that up. Yeah, it's the deli slicer, right? The meat slicer. Yeah. Okay. See, they thought of everything. Between them and the Simpsons, they got it all covered. But yeah, this line is so infinitesimal in its width that it doesn't count as part of the area. All right. So when I say something is greater than 1 under the curve, when I'm dealing with areas, when I say something is greater than 1 or greater than or equal to 1, I'm really talking about the same thing. All right. There are ways to approximate the area at a particular location. You know, if I wanted to figure out, you know, the area of the curve or the area under the curve at precisely 1. I mean, I wouldn't be able to do that without incorporating limits. But I could technically come up with something. But if I want the area to the right of it, or if I want the area to the right and I'm saying that I want it to be at least, I'm really saying the same thing. Right? Because we could never actually include the area at a particular number. All right. So I'm going to get a nice skinny line in here on this one too. Right. So infinitesimal that it might as well not even be there. But yeah, that goes under the category of mind bendy. You know, it's like, I mean, you technically learn about that in calculus 2, which is not a prerequisite for this course. So there's no expectation that you would know that stuff. But I can tell you that even my calculus 2 students have a hard time understanding or wrapping their minds around that idea. Right? So if I wanted to find the probability that Z is, so I'm going to throw in another example here. I'll take it as a typo. So probability that Z is 1. All right, so or z equals 1. It would still be a normal curve. It's just we would approach it a different way. All right, so what I would do, I don't know why I drew that horizontal line so big. I'd put 0 here. You got 1, 2, 3. -1, -2, -3. So if I just want it at 1, so again, that infinitesimal width line segment. All right, so it's so skinny that you can barely even see it. I would be looking for the area of that line. But if I'm telling you that the line doesn't have any width, how do I find the area? Because normally we think of area in terms of area of like rectangles and stuff like that. All right, so what I could do is I can kind of manufacture a little area out of this by sort of making a rectangle. And that's not a rectangle. Making a rectangle and then finding the area of that rectangle. All right. But what you come up with in terms of the area is going to be entirely dependent on how wide I make that rectangle. If I make it super skinny, I'm going to get a different outcome than I would. Now I want the shading to, you know what? I'm just going to live with this. I'm just going to fake it. There we go. I don't know. It doesn't look that good, but it is what it is. I would need to know the height of this rectangle. So I would need to know this distance here. And then I would also need to know this little teensy tiny little horizontal distance here. All right. So if I tell you that the height at this location is 2. It isn't, but let's say I tell you that the height at that location is equal to 2, and the width is, I'm going to make it 0.1 millimeters. Then I could say, okay, well, that area is 2 times 0.1, which would be 0.2. All right, I could do that. But if somebody's like, well, I was able to make my rectangle even skinnier, so its width was 0.05. So then the height is still 2. We would say 0.05 as the width, and you get 0.1 as the area. Okay? And so you get different values depending on how wide you want to make it. Now, if I keep decreasing that width so that it's next to nothing, I'm going to close in on the true probability. So let's say I do it like this. The problem is I'm going to get smaller and smaller to the point where it's equal to 0. So there has to be some other way of handling it. So the way we tackle problems like this is to use the norm PDF function. So in my toolbox, I have norm PDF. The problem with this one, well, it's not really a problem. It just doesn't feel the same as norm CDF range. But if I wanted to find the probability that Z is equal to a particular number, I would use norm PDF, put whatever that number is, then the mean and the standard deviation. All right. So that first one there's a lot of ones here, so it can be confusing. But that one is the Z equals part of things. And the 0, 1, that's the mean and the standard deviation. All right. So using this function, 1, 0, 1, I would get the probability of that particular outcome as 0.242. All right. So what we're actually getting at here when we use a norm PDF function is we're getting to the height on the curve related to a particular value. So if I put a y-axis here, so you got the x-axis here, you got the y-axis here, this height here is about 0.242. All right. So the probability that Z is equal to a particular number is 0.242. All right. But it's kind of a different interpretation because we're not talking about density anymore. We're talking about a height along the curve. All right. So what this allows for is that infinitesimal width corresponding with a height. All right. So that's probably the mind-bendiest aspect of things. And it's one of the tougher things to explain in this topic because if you have a little bit of background with calculus, it's a lot easier to understand. So I try to teach it in a way that doesn't really rely on the calculus. So that can be a little dicey. So the one last thing I wanted to talk to you about in terms of the notes before we move on to the tech assignment is how to go the other way, how to find a Z-score if you're given a particular area. Let's see, what do they do? I think the directions I gave here are Desmos directions again. So if you want to try to use it on Desmos, you can follow this stuff. But on NumWorks, it's the inv_norm function. So on NumWorks, we're using well, it's lowercase, I believe. Inv_norm. It's in the same menu. It's right below the norm CDF range. So inv_norm, A for area. Now that's particularly area to the left of the given Z-score. All right, and then mu and sigma, because we're working with standard normal curves here, this is still going to be 0 and 1. All right, but we'll get to that in a second. When I say find the Z-score corresponding to 95 or 90% to the left, that fits very nicely with this function. Now the question says 90th percentile, but a percentile is a score that is better than a certain percent of other scores. All right. So when I say I'm looking for the 90th percentile, I'm looking for the score that has 90% of it, 90% of the other data below it. All right. So I just shaded what I thought was about 90% of the graph, starting on the left. This is about 90%. I'll write it as 0.9. I'm looking for what Z is going to be equal to. All right. So kind of looking at the way we used the notation for on the previous page, what we would say is the probability that Z is less than some number or greater than some other number was equal to whatever the calculator told us as an answer. Now what we're doing is we're taking the area, which is the answer to this probability question, and working backwards to try to find the number that Z must have been less than. All right, so kind of like if you're going fill in the blanks on the previous one, on the previous page, this was the blank. We had to figure that out. Now we're going the other way. So what I would write here is inv_norm. I'd put my 0.9, my 0, and my 1. And just hit OK or execute, and you get the Z-score. So the Z-score here should be 1.282. Which honestly shouldn't be shocking, because on the previous page, we found the area that was less than, I believe it was 1.28. And that gave us 0.8997, which would have rounded to 0.9. So it was right in the same neighborhood. All right. So when we do Q3 in the next problem, that's the 75th percentile. So same idea. We're going to shade 75% of the data and find the Z-score that corresponds to that, or distribution, I should say. So this is the probability that Z is less than some number, some unknown number, and that gives a result of 0.75. So inv norm 0.7501. All right, so same computation, just change that 0.9 to a 0.75. And now we get something somewhat less, about half of the value of the previous answer. So 0.674 approximately. All right, so that number should be closer to 0 because we shaded less of the graph. All right. Yeah, and then so in terms of notes, that's all I wanted to do for tonight, because there's a lot of applications to this, but until you really have a look at this concept, like you don't want to dive into applications if you don't really have a good sense of the foundational stuff. All right, so what we're going to do now is kick over to the tech assignment, and I'll give you the overview on that. Let me just stop this recording.